So we're continuing to talk about graphs. Something that I should have mentioned from the beginning is that the terminology about graphs is very inconsistent in different sources. So if you look at other textbooks, other sources online, first of all, they may have different terminology. They may, for example, something that we call a path, maybe they'll call a circuit or a cycle or something else, or a walk. There's a lot of different terminology that people use, and they aren't always consistent. And what makes it even more confusing is that sometimes people define the same word, different people define it in different ways, right? So this word, we're going to talk about path. We're going to give a definition of it. Some people might have a slightly different definition that won't really make much of a difference, but in some small cases, it will perhaps make a difference. So that's just unfortunately the case with graphs. For some reason, more than most other areas of math, the terminology appears to be very inconsistent. I don't know why that is, but I'm just going to try to follow the way it is in the reading that I assigned. Okay, so we're going to talk about paths. So first of all, before we get into the definition itself, because the definition is very technical, let's give an intuitive idea. What's the intuition here? So the intuition is that, I could go, I can go from A to C to B to F, right? So the idea is I want to say that that there's a path from A to F. So what I'm going to do is I'm going to write that like this: A, comma C, comma B, comma F. Okay, so that's a path. It starts at A and it ends at F, and you can go from A to F. All right, so now, so let's go to the definition. So suppose U and V are vertices in a graph G, which has V and E. So here in this case, in this example that I just gave, A is our U, that's the starting point, and F is the ending point, V. So a path of length N from U to V is a sequence of vertices. So it's written like this. This is a sequence of vertices, V0, comma V1, comma V2, all the way through Vn. So you list out the vertices along the path such that U, that's the starting point, is V0. Right, so this V0 is the starting point, and V is Vn. So this, in other words, this Vn here is this Vn is the endpoint. And wait, so now that's not enough. Okay, we'll get to the rest of the definition in a second, but let me show you why the definition as we have it is not enough. How about this? How about A, B, F? Is this a path? Is this a path from A to F? Well, it's a sequence of vertices. It starts, the first vertex is A, the last vertex is F. So you might say, well, it's a path, but of course we don't want this to be considered a path because you can't go directly. There's no path A, B, F, right? You have to pass through C along the way. So you can't just go directly from A to B. You can't jump. So we want to make sure that we do not include sequences like this, right? We want to make sure that things like this do not get included. So how do we do that? So we say as follows: we say that each consecutive pair of vertices here, so V0 and V1, and then V1 and V2, each consecutive pair has to be an edge, right? So Vi, comma Vi plus 1, that set has to be an element of E for every I between 0 and n minus 1. So in other words, V0 and V1, there has to be an edge between V0 and V1. There also has to be an edge between V1 and V2. And then there also has to be an edge between V2 and V3, and so on and so on. And there must be an edge between Vn minus 1 and Vn. Right, so here there's an edge between A and C. So we have A, and then C, and then C and B. Is there an edge between C and B? Yes, there is. Is there an edge between B and F? Yes, there is. So that's why this is a path. But this other one, this bottom one, is not a path because there is no edge between A and B. Okay. All right. So now we're going to give lots of examples of paths. And we're going to talk about more properties of that paths can have. So we have some paths here. So here's the path FED. Okay, so it's a path from F to D, FED. Now the length of the path. So we have to be careful here. You might say at first glance the length of the path is 3, but go back to the definition, right? The definition says that a path of length n is a sequence of vertices starting from V0 going through Vn. So in other words, how many vertices are in this sequence? Not n, right? There's n plus 1 vertices here because we're starting from 0 and going through n. So there are n plus 1 vertices here, but the path is a path of length n. So this path, for example, which has 3 vertices, it has a length of 2. And the idea is what you're really doing is you're counting the number of edges that the path travels along, right? So when you go from F to E and then to D, you're traveling along 2 edges. So that's why the length is 2. Okay, and then now there's also something here, simple path and cycle. We'll come back to those because we didn't do those definitions yet. Okay, another path is DEF, right? So we can go FED, but then a different path is DEF. We can go from D to E to F. So it's a path from D to F, length of 2. DF, that's also a path. Then D, A, C, B, F, that's a path from D to F. So notice there are lots of different paths from D to F. And this particular path is a length of 4. Here's another one. D, A, C, B, F, D, E, F, D, E, F. So this is a very roundabout path. We're looping a little bit, but that's fine. We're allowed to loop. And this is a path from D to F, and right, because it starts at D and it ends at F. If you count these vertices, there are 11. So the length of the path is 10. Next, DEFD. DEFD, that's a path from D to D. Okay, so you can have a path going from a vertex to itself. DEFD. So remember, you cannot have an edge going from a vertex to itself, but you can certainly have a path going from a vertex to itself, right? So DEFD, that's a path starting at D and ending at D. And the length of the path is 3. We can also have FEF. Notice what we're doing here, we're kind of like backtracking. We're going from F to E and then going back to F, but that's fine. It's a sequence of vertices starting at F and then going to D and then ending at F, right? So FEF, that's fine. It's a path from F to F with a length of 2. How about just D? How about just D this? Is that a path? Is that a path from, well, is that a path? Well, it is. It's a path from D to D, and the length of the path is 0. So let's go back to the definition. So a path, we have to make sure it fits the definition. A path of length n is a sequence of vertices. So there are n plus 1 vertices. So if we're talking about a path of length 0, there's going to be 1 vertex here because this always has n plus 1 vertices. So if n is 0, then we're going to have 1 vertex. So for example, vertex D. And the condition is such that, well, we have to start. The starting point is V0. The ending point is Vn. Well, in this case, there's V0 is the same thing as Vn, right? The first thing in the sequence is the same thing as the last thing in the sequence. Okay, so this is a path from D to D. It's fine for a sequence to just have one thing in it. And we need to make sure that there are edges between every pair of vertices for each I between 0 and n minus 1. Now, in a case where n is 0, is there any value of I between 0 and n minus 1? Answer is no, because n minus 1 would be -1. So if you're looking for a value here that's above 0 and less, well, greater than or equal to 0 and less than or equal to -1, there's nothing there. There's no possible value of I here. So we don't have to have any ordered pair like this because there are no values of I, right? We have to have we would only have to have this if there are valid values of I. But in a case where there's just one vertex, so and that's the whole path. That's the entire sequence. We satisfy that condition and we're done. So so this is a path of length 0. All right, next. D, E, F. D, E, F, D. Okay, that's a path. Starts at D, it ends at D. Length of the path is 6. Okay, we can loop around twice. That's fine. How about this? D, E, F, D, A. Okay, D, E, F, and then back to D, and then to A. That's a path from D to A. Very strange path from D to A. I could have gone straight from D to A, but I decided to go D, E, F, and then back to D, and then to A. But that's fine. It's a path from D to A. And the length is 4. Then A, C, B, F, D, A. Okay, A, C, B, F, D, A. That's a path. A, C, B, C, B, A. Okay, A, C, B. Hold on, did I make a mistake? No, sorry, A, C, B, C, A. That's one. A, C, B, C, A. That's fine. We're backtracking, but that's not a problem. Okay, now 2 definitions. A simple path is a path that has no repeated vertices. Right, so some paths have repeated vertices, some paths don't. So a path that has no repeated vertices is a simple path. So let's go through these paths again. So FED, no repeated vertices, so it's a simple path. DEF, no repeated vertices, so it's a simple path. DF, no repeated vertices, so it's simple. This, no repeated vertices. This has a multiple repeated vertices, so it's definitely not a path. It is a path. It's definitely not a simple path. I'm sorry. This is all whether it's a simple path. This is a simple path, simple path, simple path, simple path. This is not a simple path. It's still a path, but it's not a simple path. By the way, as usual, the terminology is very different in various sources, right? So some people might call this, instead of a simple path, they might call this a walk or a circuit or this or that. There's all sorts of terms. Okay, next, DEFD. Is this a simple path? No, because the D is repeated. FEF, also not a simple path because the F is repeated. Is this a simple path? Yes, nothing is repeated. There's just one thing, but it's never repeated, obviously, because there's only one thing. So how could it be repeated? This is, there are some things that are repeated. This has repeated D, so it's not simple. It's not a simple path. This has an A that's repeated, so it's not a simple path. This has A and C that are repeated, so it's not a simple path. Okay, another definition. A cycle is a path, V0 through Vn. It's a sequence of vertices, V0 going through Vn, such that all of V0, V1, V2, all the way through Vn minus 1 are distinct. Distinct means they're different from each other, meaning there is no duplicate. So among the first n vertices, starting from the first vertex V0 and going through Vn minus 1, there are no duplicates. They're all distinct. And we also need to make sure that V0 equals Vn. The point is the cycle is a path that starts and ends at the same place. Okay, and in between there cannot be any duplicates. Okay, again, in English, a cycle is a path that starts and ends at the same place, and in between the starting and ending, there are no duplicates. So let's go back through these. So is this a cycle? No, because it doesn't start and end at the same vertex. This is also not a cycle because it doesn't start and end at the same place. And this is also not a cycle for the same reason. This is also not a cycle for the same reason. And the same thing here. This starts and ends at the same place. And aside from the beginning and the end, there are no repeated vertices, right? So these first 3 vertices are all distinct. Now, the first and the last are copies of each other, but that's fine. That's still okay for a cycle. I mean, it's necessary actually for a cycle to start and end at the same place. So this is a cycle. This is also a cycle. This is also a cycle. It starts and ends at the same place, and in between there are no repetition. So it's a cycle. This starts and ends at the same place, but there is repetition in the middle, so it is not a cycle. It's not a cycle. This is not a cycle because it doesn't start and end at the same place. This is a cycle. Starts and ends at A, the same place, and the first, among these vertices, there are no repetitions. There are no repetitions. This starts and ends the same place, but there is repetition in the middle. So it's not a cycle. Okay, so some more definitions related to the ideas of paths. So we're not going to be talking about simple paths or cycles anymore here, but we're going to be going back to the idea of a plain path. So a vertex V is reachable from vertex U if there is a path from U to V. Also, in this case, we say that U and V are path connected. The point is they're connected, but they're not adjacent to each other necessarily. Maybe they are, maybe they aren't, but they don't have to be adjacent to each other, but they are connected by a path. And the idea is one vertex is reachable from another. So, F is reachable from A. Okay, so A and F are path connected. They're not adjacent to each other, right? You can't go straight from F to A. They're not adjacent to each other, but they are path connected because there is a path connecting them. But let's say F and H are not path connected, right? So because there is no path connecting them. Okay, so A and F are path connected. Vertex F is reachable from A and vice versa, right? So F is reachable from A because if you start at A, you can reach F. Okay, so F is reachable from A, and also vice versa, right? A is reachable from F. What does that mean? It means if you start from F, you can reach A. So A is reachable from F. And A and F are path connected. And another definition, the connected component of a vertex V is the set of every vertex that is reachable from V. Okay, so what is the connected component of C? Well, it's the set of every vertex that is reachable from C, meaning the set of every vertex that is path connected to C. Okay, so, well, A is path connected to C, B is path connected to C, C is path connected to C because there is a path C, just the sequence just containing C, that's a path. There's a path from C to D, there's a path from C to F, there's a path from C to E. So all of these things in this part of the graph here are the connected component of C. So this is one big connected component. This here is another connected component. And then G is a connected component all by itself, right? So there's a path G just going from G to itself, right? But there's nothing else that's path connected to G. So at any rate, the connected component of C is, as we said, A, B, C, D, E, F. So there's a path going from C to each of these vertices. There's a path from C to A, there's a path from C to B, there's a path from C to C, there's a path from C to D, from C to E, and from C to F. So this set is the connected component of C. The connected component of H is, as we said, H and I. There's a path from H to itself, and there's also a path from H to I, and that's it. And then also, as we said, the connected component of G is just the set G. One more definition here, a graph is a connected graph. Okay, so we talked about connected component, but now connected graph, a graph is a connected graph if each of its vertices is path connected to all of its vertices. So this graph here is not path connected because, for example, there's no way to get from B to I, right? So in other words, this is one big graph, but it's not a connected graph. If we would remove H, I, and G from this graph, right? So if we would just be left with this part here, then it would be a connected graph because within this part, everything is connected to everything else. But as we have it now, this graph is not a connected graph.